All right, we're rolling. I've got a corporate sponsor now, I realise, haven't I? Okay. So, again, covering stuff that you should have done last year. Does anyone remember anything about infrared from last year? What it is, what it does, what it tells you. Mostly what it tells you, really. That's what we want to know. If I stick a substance into an infrared spectrometer, I get out a pretty graph. What does that tell me about the substance? What do I learn?
Is it the type of bonds?
Go a little bit further. Remember, this is organic chemistry we're looking at chiefly. It's organic substances that we're going to stick in our spectrometer.
Don't you get spikes at carbon single bonds and carbon double bonds, stuff like and things like that?
Yeah. So if the spectrum tells me about specific bond types, what's the information I learn about the molecule? What am I finding out? Anyone feel free to jump in. Yeah, we use the wavelengths to work it out. I'll come to the details in a moment. But what's the key thing we're trying to learn here? Yes, we get absorbance at a particular wavelength or frequency, and that enables us to work out a particular bond. What does that tell us about the molecule?
What's in it?
In terms of?
Its structure.
In terms of? Who said that? Functional group. Thank you. Okay, so we're looking at a way of learning functional group. That's the whole focus of infrared. So if your molecule is butan-1-ol, it's not going to tell you the butan bit, it's going to tell you the alcohol bit. It's going to say this has got an alcohol in it. That's what we're going to learn from that. All right. Now, the nuts and bolts of that, you don't really have to know this, but I think it helps a little bit to have a bit of knowledge about infrared, just so it makes some sense. So chemical bonds, they're not static. We tend to draw, chemical bonds as a line, don't we? Or we make them out of plastic, and they're hard and they're solid. But actually, chemical bonds will be moving all the time. The atoms will be in motion all the time because they've got energy, like all particles. And we can imagine them as being a bit like springs. They vibrate and they stretch and they twist. And the energy that causes the bond to vibrate is in the infrared part of the electromagnetic spectrum. So if we shine infrared light on a molecule at a range of frequencies, then certain functional groups will absorb that light at certain frequencies, telling us what they are. If you flick to the back of booklet 20, there's a bunch of frequencies on there. That's the table which might be familiar from last year. So just a very quick overview, and again, no one's going to ask you this in the exam, but a very quick overview of how it works. So we start off with an infrared light source. We split it into two parts. We send part of it through your sample, and the other half goes through a reference. The reference and the sample then get analysed by the detector, and you get a readout which shows which parts of the light are being absorbed. Which parts of the light. That's a very sort of simple overview. Now, so we're gonna see a spectrum where parts of the light have been absorbed, and I'll talk about an actual spectrum in a moment. Units of frequency are a bit odd. If you think about the relationship between frequency and wavelength, what's the equation there? Come on. Yeah, that's right. So I'm going to do it the other way around, if that's all right. Frequency is 1 over wavelength, yeah? So if I measure my wavelength in centimetres, then a measure of frequency would be 1 over centimetres, hence centimetres to the minus 1 as the unit. So it's a unit of frequency, but it's an unusual one. It's not one that they would ever use in physics. chemists love coming up with odd units that are non-standard, non-SI, and it's known as wave number. I'm telling you that so you're going to see it on the spectrum, and it's not going to alarm you. You're not going to go, what on earth is wave number? It's just that's the name that they've given whoever invented infrared spectrum. So CH bonds, for example, stretch at between 2850 to 3000 centimeters to -1. So you're going to see that quite a lot, given that almost every organic molecule has some CH bonds in it, right? But just before we go on and look at the spectrum themselves, let's have a look at this rather fun page of Wikipedia. This just gives you an idea of how complicated just something simple like a stretch is. If you've got a carbon with 2 hydrogens on it, they can stretch symmetrically. These all look like workouts to me. Or asymmetrically. Yeah. Scissoring, which, if you put a kettlebell in each hand, I'm sure that would be a really good workout there. Rocking, which looks like a sort of, I don't know, some sort of fan at a concert. Wagging, which is coming and then going away. And then twisting, which is really hard to do when you're an old idiot like me. But even just 2 hydrogens can absorb infrared energy in 6 different ways. That's just 2 hydrogens. So if you get a complicated molecule, well, not even a complicated, I mean butane, C4H10, you've got 10 hydrogens all doing their thing. You're going to get a lot of peaks. Okay. Yeah. So spectrum looks like this. So along the bottom here we have wave number. Just to make it a little bit more complicated, it's not a linear axis, it's a logarithmic axis. So you'll notice that 4,000 and then 3,000 is that distance, but then it gets bigger. That's 1,000, that's only 500. The axis is kind of stretching as you go to the right. On the left here we have usually some fairly clear peaks which we can identify easily. As I said, 2850 to 3000, that's CH, and there they are. There's a whole bunch of CH peaks there, CH stretches there. And this is pentane, so we've got a lot of them, 12 of them. And you can sort of see there's lots of different peaks all kind of overlapping there. So we call them peaks, even though they're kind of dips. But, if you turned it upside down, they'd be peaks, wouldn't they? And what we're measuring here is the amount of what's called transmittance, which is kind of the opposite of absorption. If you have 100% transmittance, that means all the light has gone through the sample and come out the other side. 0 transmittance means that none has come out the other side. So you could say that 0 transmittance would be 100% absorption, and that would be 0% absorption. So this kind of line along the top is most of the light is going through the sample, and then it's getting absorbed in very particular places. So these are absorptions. So all we need to do is look along the bottom here and see the peak and read it off, and then you can go and look it up on your table that you get given in the exam and find the frequency for that peak or the wave number for that peak and identify it. Now I put CH up first. I think, no, it is done. CH is on your list, but I put it up first because I don't really tell you an awful lot about the molecule, does it? CH. It tells you it's an organic molecule. Yay! Doesn't really tell you anything about the functional groups. What we could learn from this spectrum is because there's an absence of peaks, kind of all around here. There is no functional group in it, right? Pentane doesn't have a functional group. It doesn't have an alkene or an alcohol or a carbonyl or anything useful. So that would tell you immediately, looking at that, that's probably a hydrocarbon. Below 1500, this kind of right-hand side of the spectrum here, you're not required to identify specific peaks in that area, even though the data you're given on the data table goes well into that region. Carbon-carbon single bond, what's that, 750 to 1100, well that's quite a big range. It's anywhere in there, so there's probably some carbon-carbon peaks in there, but it's not very easy to identify specific peaks, and this part of the spectrum can get very messy, as it is here, with all sorts of little peaks denoting all sorts of things. So as far as you're concerned, really below 1500, you're not going to be asked to identify any peaks there. We call it the fingerprint region because it usually gives us quite a complicated pattern of peaks, and because it's complicated, we can look it up in a computer database. So that particular pattern would identify pentane in the same way that we can look up a fingerprint, right? Hence the name. Okay, any questions so far? Again, you should have done this or some of this last year. So just a summary of the notes there. So light from an infrared source passes through the sample. Some of the light is absorbed by specific functional groups or specific bonds. Units of frequency are centimeters to the -1, known as wave number. And we can see individual functional groups, but below 1500, we're going to ignore that. If you were in university, you'd probably spend hours looking through tables identifying all those peaks, but you're not expected to do that. Okay. What you are expected to be able to do is identify a few fairly simple functional groups. And we'll start with OH alcohol. So OH alcohol, whatever it says on here, OH alcohol 3230 to 3550, well, that's well above our CHs. We can see lots of CHs there. We know they're always going to be there, so we'll ignore those. But here is this very new, big, broad, strong peak. Very, very clear. Again, below 1500, there's a whole bunch of stuff going on, but we're going to ignore that. The information we can get from this is that we're looking at an alcohol. Okay, it's propan 1-ol that we're looking at. Propan 2-ol. Looks very similar. If I flick between them, you can see the difference in this end. If you keep your eye on the fingerprint region, you can see that's changing a lot for propan 1-ol to propan 2-ol. But over here, it's hardly changing at all. That OH is staying as a big, broad peak, very identifiable, very clear. So one of the things you're going to you need to know for infrared is not just kind of where the peak is, it's also to have a feel for what it will look like. OH is always going to be a massive, wide, broad peak. Okay. Let's look at some others. So we've already covered CH. I'll come back to OH acid in a moment. The carbonyl peak is right in the middle of the spectrum, 1680 to 1750, and it's usually strong and sharp. There it is. It's again usually right in the centre of the molecule. Sorry, right in the centre of the spectrum, and it's usually pretty sharp, and it's usually very strong. So this is a carboxylic acid. This is butanoic acid. Of course, butanoic acid has an OH in it as well. As luck would have it, the OH acid absorption is different from the OH alcohol absorption. You'll notice that they're in different places on your table, on the table A there for the data. And in fact, it's sort of shifted to the right compared with alcohol. It's around about 3000. In fact, it's almost sitting on top of the CHs. These are the CHs poking through the bottom of a very broad OH acid peak there. So for carboxylic acid, we're going to see an OH sort of slightly to the right of an alcohol, and we're going to see that carbonyl peak there. Now, unlike OH, carbonyl isn't going to shift around much, and you're not going to be able to narrow it down to a specific functional group. So carbonyl is not really a functional group at all. It's just a carbon-oxygen double bond. Of course, we've got lots of carbon-oxygen double bonds. We've got acids, we've got acid chlorides, we've got amides, we've got one of those. What's that called? Anhydride, thank you. And then of course we haven't got aldehydes and ketones as well. So the carbonyl group doesn't quite tell you which functional group it is, and you're not expected to tell the difference either. You couldn't say, oh well, that's exactly 1710, so it must be an acid. That's not going to happen. There's another one again, right in the centre of the spectrum. This is just butanone, butane 2-one. Big strong peak, sharp, dominates the spectrum almost all the way down to the bottom. There's our CHs there. So that the important thing is to be able to get a feel for what a peak should look like. We've looked at OH, carbonyl, C double bond O, good strong sharp peak middle of the spectrum. But I'll often get people say, oh, but what about this? There's a peak here. Does that mean it's got an OH in the molecule? Well, no, because if it had an OH in the molecule, it would be a massive broad peak like that. It wouldn't just be a bit of something. I mean, there's obviously something there, but it's not enough to be a full OH peak. Does anyone have any idea what that might be? It's in the right region of the spectrum for OH. I'll hold this for long enough. Do you think Tim Hortons will sponsor me? That'd be good, wouldn't it? Great coffee. Available on... Oh, no, never mind. Yeah. Okay, so the reason that the OH peak is so broad is because of hydrogen bonding. Thank you for bringing that up. If you think about what a hydrogen bond is, you've got whatever's going on there. You've got a bond between an H delta plus and a lone pair on an oxygen, and what that can do is sort of pull the hydrogen away, so we end up with a hydrogen almost acting like a bridge between the two oxygens, which means this bond can extend over quite a range of frequencies, which means that the OH peak ends up being very, very broad. So that's where hydrogen bonding comes in. Anyone? I'll give you a clue. It's an impurity. It's not something that should be there. What impurities do we know that have lots of OH in? Like on a university challenge here, there's a little bit of consultation going on. Any ideas? Yeah, it's water. Yeah, it's probably just ever so slightly wet. Of course, a very, very tiny amount of water. Given that you often only analyse milligrams of sample anyway for infrared, so a very tiny amount of water, given that OH absorbs so strongly, will often get onto our spectrum. That's another one. That's butanal. Again, difference between butanal and butanone is not much. You're not going to be able to use an infrared spectrum to distinguish between butanal and butanone. In just the same way you couldn't distinguish between propan 1-ol and propan 2-ol. It's going to tell you the functional group or the particular bond. It's not going to give you more information than that. Okay, if you can identify or distinguish OH alcohol, OH acid, and spot a carbonyl, you can probably answer 90% of A-level questions that are out there on infrared. Seriously, most of them come in on those three there. And again, knowing what the peaks look like or supposed to look like will help you spot them as well as just reading off the numbers. There's a couple of others that have crept in over the years, and they're on the back of the they're on the back of the booklet there. So let's just have a look at those. Nitrile is the first one. If you look at the range for nitrile, 2220 to 2260, that's a very narrow range. Compared that with the range given for an alcohol. Acid, 2500 to 30. That's a range of 500 centimeters to the 1. This is a range of 40. Yeah, very sharp. Very sharp. There it is. There's a carbon-nitrogen triple bond in nitrile, and it's appearing pretty much bang on 22 something, 2230, 2240, and it's very sharp. So that's quite an easy one to spot. It's not always as strong as that. I've seen smaller nitriles in my time, but it's very sharp, and it's usually bang on those numbers. So if it does appear, that it actually can be quite an easy one to spot. You've just got to think it there. Again, bit of water. NH. Okay, so NH can be a little bit confusing, which is the main reason why I say it. This is propylamine or aminopropane. Confusing because it's in the same part of the spectrum as the OH. But this is where knowing what a peak should look like helps. OH peaks are always massive and broad. NH peaks are a little bit more subtle, smaller. And what's really nice here is we've actually got 2 peaks. It's NH2, isn't it? I don't know if that's why we've got 2 peaks, but there's more than one atom there giving us an absorption. So we're getting more than one frequency of absorption. So we just don't want to get too confused between OH and NH. They're in the same part of the spectrum, but they look quite different. NH is always smaller than OH. Did I put a carbon-carbon double bond on? Yay, I did. Yeah, that's quite a subtle carbon-carbon double bond. But again, it's sharp and it's in the right place. What does it say? 1620 to 1680. That's pretty close to carbon-oxygen double bond. But you couldn't confuse the two in terms of look. Right, carbon-carbon double bond is small and sharp. Carbon-oxygen double bond would be right down here. It would be the strongest peak in the spectrum. So again, knowing what the peak should look like will help you identify it as well. So carbon-carbon double bond, small and sharp. Did I not put that on my list? What have I done? I'm hitting the wrong button. That was not helpful. Oh no, I didn't. Okay. So carbon-carbon double bonds should be on my list. I'll put that on. Yeah, small and sharp. Okay. Any questions? We'll have a look at a couple of things then. Tell me about A. Now again, you can't use this spectrum to say, oh, I know it's such and such 3, 4, such and such dichloro. You're never going to be able to do that. But what can you tell me about A?
No functional groups.
It's got no functional groups. It's got a lot of white space here and here, and some stuff going on there that we can't understand. But what we can see most of all is it's got no functional groups. So it's probably an alkane. That can be useful as well, yeah? Knowing that it doesn't have functional groups tells you something about it. Yeah, so that was isopentane. What's that? Methylbutane is what that is. Okay, so no visible functional groups. That's probably a takeaway from that spectrum. And these questions could come up. They could give you a range of spectra and ask you like a multiple choice question. You know, which of those is the alkane? So it's sort of staring you in the face because it doesn't have any peaks. Yeah. Apart from your CH, but you're not going to get that confused again. What's B? I've seen B already, but it doesn't really matter. It's a carbonyl. And again, you can't be more specific than that. It could be an aldehyde, it could be a ketone. It can't be an acid, of course, because we don't have a peak over here, although it does look like it got a bit wet. But it's definitely a carbonyl. And we can't be more specific than that. So that was pentanone, pentan-2-one. Yeah, and if that's all the information you need to get from that, that will probably help you solve the problem. So you've done quite a lot of these starters. At the beginning of the question, come up with a molecule which has the formula C4H10O, which has stereoisomerism or whatever it is, and this could sort of play into that. So molecule B has this molecular formula and has stereoisomers. What is it? And you've immediately got some information there. What do we think? Go on, Ben. Looking at that there. It's confusing that, isn't it? I'm just looking at that and going, well, okay, that's definitely an alcohol. We can definitely take that away. It's actually just an alcohol, and I don't quite know where that's come from. It's actually just ethanol. But that's around, where's that, around 16? It's around about 1650, which kind of doesn't really. Hey? Yeah, but again, carbon-carbon double bonds are small and sharp, and it's not quite big enough to be a carbonyl. I find that a little bit confusing. But hopefully the examples they give you in the exam won't have random peaks on, which are confusing. I might even edit that out. No, I'm not going to do that. One more. Oh, it's got the answer on it, so that's helpful. Notice here. I need to do my PowerPoint again. So we've got a nitrile there. Hopefully that was very obvious, but don't miss the alkene there. Carbon-carbon double bond. So this is an alkene and a nitrile. Okay. Well done. Brilliant, Harris. Well done. Is that enough? Yeah. Okay. That was the end. Right. What am I going to do? I'm going to stop the camera before I continue to make a fool of myself.